Hello everybody and welcome back, or welcome if this is your first video watching. We're going to be looking at the 2004 Euclid contest question number 10. And if you are just joining us and you want to try this question for yourself before watching the video, you can click the link in the description, get a copy of this contest, or really anyone who's watching, you can click the second link and go to the University of Waterloo's past contest. You can try just about anything there. And I've got videos for some of them. I'll have more videos in the future as we keep going. We're just on 2004 right now. That said, we're going to take a look at question number 10, so let's dive right in. So this should be the hardest question in the contest, but let's take a look here. A Skolem sequence of order n is a sequence, S1, 2, all the way up, so there's 2n integers, they say, satisfying two conditions. For every k, so for every k in the first n integers, there is exactly two elements, si and sj, with si, so two of them are always going to be equal to 1, two of them are always equal to 2, two of them are always equal to 3, okay? And our second condition here, if si is equal to sj, so if both of these are 4 or 5 or something, then their difference in the indices is that number. So if the two numbers that are 4 away, the two numbers that are 6 are 6 away. For example, 4, 2, 3, 2, 4, 3, 1, 1 is a Skolem sequence of order 4. You notice how we've got 1, 4 here, then 1, 2, 3, we've got our fourth 4 spaces away. So the 1s have to be beside each other, the 2s have to have one thing in between. Interesting. As an aside, as I'm thinking about this, as I'm looking at this question, it reminds me of a concept called a Langford kebab, which is not the same. A Langford kebab is you do similar sort of things. There's 2 of each number, but in between the 1, there must be one number. In between the 2s, there must be 2 numbers. Whereas here, in between the 1s, there must be no numbers. In between the 2s, there must be one number. It's interesting. I don't know if any of my knowledge of Langford kebabs will particularly help. I know that there are kebabs for size 3 and 4 and 7 and 8, and there's a limit to them. Where I learned this, by the way, was not in any math class. There's a wonderful show I found called School of Hard Sums. It's by an Irish-British comedian named Dara O'Brien. You can find some of the videos on YouTube. I do encourage you to go look at that. It's an interesting show. They do math problems. They have comedians on who try and solve math problems sort of the dumb way. And Dara O'Brien, I think he has a PhD in math. He tries to do it the mathy way, and is a math expert. And it's actually a good show, even for people. Like, I have friends who've watched it, and they're non-mathematicians. They found it interesting. Anyway, plug for that show over. But this Skolem sequence here does sort of remind me of Langford kebabs. And I think if I were to renumber things or relabel things, I'd get the kebabs I want. But let's take a look here. So just that's the sort of thing that pops into my head. Something worth looking at on your own time if you want. So we got a Skolem sequence of order 4. A part, list all Skolem sequences of order 4. So we've got this one. And nothing that says we can't just reverse it. So I think whatever Skolem sequence we find, we can always reverse it and get a new one. Unless there's a symmetrical one. I don't think there would be. No, I'm pretty sure you can't have a symmetrical Skolem sequence, because I'm just trying to think about it. The 1s would have to be placed in the middle, the 2s can't go around them, the 3s would have to go around them, and the 2s would be off on one side or the other. Interesting things to think about, though. List all Skolem sequences of order 4. Okay, well, I don't really have anything to go on. Even if I did remember much about Langford kebabs, I shouldn't be using that, because I want to approach these questions how anyone might have. So, what have we got? We've got 8 positions. And we got to put the numbers in there. And, what should we do? Because part A, nowadays at least, is usually about getting used to the brand new concept that they've thrown at you. Nowadays, usually 10 is not here's some complicated geometry problem. Usually 10 is, here's some brand new concept with a fancy sounding name that's got these rules. How quickly can you adapt to this situation? And usually A part and a little bit of B part is getting you used to the rules, and then you figure out the patterns, and you use that to make generalizations and prove results for C part, that sort of thing. So we're not meant to be doing this one fancy. It's probably going to boil down to casework. I think that's what it is. So we've got to place some numbers. So I can think of sort of two logical ways to do it. We can start by trying to place the ones, because we could have ones here, or we have ones here, but we're going to have lots of different spaces for the ones. Whereas I think if we place the big numbers first, so for example the fours can really only go 1, 2, 3, 4. Or we could have the fours spread out like this, or the fours spread out like this. Or, because here, if we did the ones, we'd have, I think, 7 different places for the ones, but now with the fours, we only have 4 different scenarios to consider. Okay. So it's going to be casework, I think. And I think we could probably discount these 2 cases because they're just going to be symmetric versions of these ones. So it's a written question, so we do need to start writing some of this down. Let's say determine Skolem sequences by placing the fours first. Note we have 4 potential places for fours. But since it is, I'm going to say, clear from the definition, if you don't think it's clear, you can add a little extra line of dialogue, or you could in that sort of situation. But I would say it's clear from the definition. That the reverse of a Skolem sequence is a Skolem sequence. We will only consider the first 2 cases. Okay? We explain what we're doing, why we're doing it. If you want to explain why you're doing the fours first, that's fine. Although you really don't need to. You never need to explain the intuition or the inspiration for results. You just need to explain why they are logically true and why other things wouldn't work. That's all you need to do. Okay, you don't say, gee, I thought about placing the ones, but then I realized that was going to be a lot of work, so I decided I was going to place the fours since there's less work to do. Don't need to say that. You just say, we're going to start by placing the fours. Here are our cases. We can get rid of 2. So here are the other 2 cases. Let's do the casework. That's all. Okay? Cuts you down on writing, because sometimes on these competitions, it takes a lot of time to write out your results and your concepts. Well, let's start experimenting. 3, 4, 5, 6, 7, 8. Okay. So 4, and we got to have another 4 here. I'm going to switch pen color because I'm just going to mess around a little bit. Where could the ones go? Actually, should we be placing the ones second? We avoided placing the ones first, and there's lots of places the ones can go. How about 3s? We could have 3 here, 1, 2. Well, we can't have a 3 there. We could have a 3 here and a 3 here. Or we could have a 3 here and a 3 here. By the way, drawing the picture like this is perfectly fine. 2 cases for placement of the 3's. Let's investigate those two cases. 2, 3, 4. 1, 2, 3, 4. We've got our 4's here. We've got our 3's here. We'd have our 2's would have to go here, and our 1's would have to go here. I might say 1's must go here. Because over in the spots where the 2's were, there weren't 2 side by side. So we had a problem. So 4, 2, 3, 2, 4, 3, 1, 1. And 1, 1, 3, 4, 2, 3, 2, 4 are Skolem sequences. Okay. Do remember, we have to reverse. We said it was okay to reverse. We told them we only have to do so much work because we can just reverse all of them. You got to follow through on that. They asked us to list all of them. You got to list them all. You don't say, okay, these ones and their reverses. Show the reverses. I mean, you only have to write 8 numbers. Okay, so that was one, and I imagine the other one will probably go as smoothly. So 4 here, and then the other one was the 3's here. And then, yeah, so the 1's have to go here, and then the 2's have to go here. So 4, 1, 1, 3, 4, 2, 3, 2, 2, 3, 2, 4, 3, 1, 1, 4 are Skolem sequences. Okay, now we had the other case, and sometimes it's a good idea to label your cases. Because it's not entirely clear. I'm just drawing sort of dashes and putting numbers on them, so you might want to separate and say, you know, this case, where the 4's were spaced out like this. Okay. And again, we ask where the 3's go. And if you want to write, you know, first question we ask is where the 3's go. Go right ahead. We could, oops, I was putting my possibilities below, wasn't I? So we could have 3 and then 1, 2, 3. Can't have a 3 there. We could have 3, 1, 2, 3. And we could have 3, 1, 2, 3. We could have 3, 1, 2, 3. Yeah. So this one not allowed, but the others are all perfectly fine. I can already see that this particular case here is not going to leave us, because we're going to have a blank over here, and then we're going to have 2 things. You can't put a 2 there, you can't put a 1 there, so that one's already going to fail. So I'm thinking we have, we definitely have at most 8 Skolem sequences, but I think we might have exactly 8. I'm willing to be proven wrong. Only 3 cases for where to put the 3's. Two, 3, 4, 5, 6, 7, 8. We'll do this one first. 3, 4, and then the other 3 goes here, and the other 4 goes here. And I would say it's pretty clear we got to have our 1's here and our 2's here. If you are explaining at each stage, I would say you can stop probably explaining it at this point, because it's clear where these numbers are coming from and where the 2's and the 1's have to go. 1, 1, 4, 2, 3, 2, 4, 3 are Skolem sequences. Alright, and then it was the 3 sort of in the middle, and then the 3 right after. Those are our other 2 cases. 1, 2, 3, 4, 5, 6, 7, 8. Our 4's are off by 1. And then we couldn't have a 3 here because the 3 would go there, so we put the 3 here and a 3 here. And we are going to have a problem. So I would explain the problem. No No pair of spaces for the ones. I would say that's enough. You might want to illustrate it, but I think you've got bigger fish to fry in this question. Then this one is likely only worth 2 marks, maybe. Actually, probably 3 marks. If I had to guess, just based off of having marked some of these things in the past, I would guess this might be worth 3. Probably 1 mark for getting a Golem sequence different than the one they gave you. Probably 2 marks if you had 3 or more, and probably the full 3 marks if you had all of them correct with no extras, that sort of thing. Just based on how they've done other sequences and other numbers, just when they ask you to enumerate them or list them all out, that sort of thing. Anyway. Okay, so no Golem sequences there. And then the one that I was pretty sure won't do anything. Actually, was this the one I was pretty sure won't do anything? Yeah, we have one more case. And then it's the 3s at the very end. That's what we're looking for here. But this also, the 1s have to go here. Ones must go here. 2s are too far away. So, there were only 6. I would have thought there'd be 8. Interesting. Okay, so you might want to go back and round them all up. 4, 2, 3, 2. Yeah, I'm not going to waste time in the video just rounding them up for you guys. You can see them. But we've got 6 of them, and I would, after having written them out, I would probably list them all together. It makes the life for the markers a little easier. You know, here are all my Golem sequences together. Anything else you saw, if you just sort of survey marking, just going through it quickly, I've got all 6, there it is. Because that's likely where you're getting the marks, is not so much your reasoning. Because let's be honest, this was just casework, and do I understand the definition? There's not a whole lot of like complicated, intricate, logical reasoning here going on. It's just, do these numbers fit here, or do these numbers fit here? So I would bet in the marking room it was just, how many do they have? That sort of thing. So just put them all together. It makes your work a whole lot neater, and it saves us time when we're marking these things. But there's all 6, and we did exhaust everything. We showed exactly what it is, so if they do care about the written work, we have exhausted everything. And it can only be these 6. All right, back to the question. We're looking at B part now. Let's flip the page first. So we listed all the Golem sequences of order 4, and this is where B and C are where we should probably start understanding properties of Golem sequences and how to generate them, or how to count how many there are, that sort of thing. Just before I read 6, I'm thinking that maybe maybe like Langford kebabs, there's only a certain number that can be, there can't be a 5 Golem sequence of order 5. Or maybe there's a way to take an even Golem sequence and make 2n plus 1 out of it, or like a Golem sequence of 2n plus 1 out of that. There might be some weird tricks that we're going to notice or need to notice for B and C. That's the sort of stuff that we should be thinking out. When you do a Euclid, you should always try and do at least 10a, because it's likely a simple listing question like what we just saw. Okay? That wasn't particularly difficult, certainly not as hard as, say, 8 or 9 or even 7. It was, do you understand the definition? Can you do this really simple application of the definition? It's B and C that'll get you. But always try A, because that's just 2, 3, sometimes even 4 marks just begging to be gotten from just understanding or being able to read. Okay? But enough dilly-dallying, let's actually read B part. Alright, determine with justification all Golem sequences of order 9. Oh, goody. Well, hey, that would, I didn't intend it, but that would be 2 times 4 plus 1. All Golem sequences of order 9 which satisfy the following 3 conditions. Oh, okay. S3 is 1. S18 is 8, and between any two equal even integers, there's exactly one odd integer. Okay. I might as well read C while I'm at it, because most of the time you want to be using what they using what they ask you to do in part B to understand properties that you'll need for part C. That's the mark of a good question. When you already have an idea of how to generalize from B to C. So let's see, what is C? Prove there is no Skolem sequence of order n if n is the form 4k plus 2 or 4k plus 3, where k is a non-negative integer. So this is very similar to what I said at the sort of the start when I was talking about Langford kebabs. I didn't really describe them fully. There's something you can look up if you want. But Langford kebabs, you can have 7 and 8, but you can't have a 5 or 6 size Langford kebab. And so I think this is a very similar concept. If I knew the proof for Langford kebabs, I'd probably be quite set. I honestly don't know it. But that's something we're going to have to be doing in C. And that doesn't really seem to connect right now with B. But let's do B, and maybe something will jump out at us. Maybe the way we do B will help us with C. Or maybe it'll just be a brand new thing. Okay. So, sequences of order 9. So there will be 18 numbers to place, and it looks like S18 has got to be 8. So the last thing has got to be 8. That forces 8 to go in a certain place, and I think we can use that information. Oops, we're still on green. Okay, so for B part here, I would start by saying something like such a sequence of order 9 has 18 integers. So S18 being 8 forces S10 to be 8. Since there is no S26. Once you've placed one of the numbers, you're sort of forced to have the other one in a particular position. And so since it's got to be S18 is 8, S10 has to be 8 as well. So what are we looking at? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I did not actually think I was going to get that through. So 18, there's 15, 12, so this guy's got to be 10. 1, 2, 3, 4. Okay. So there is such a sequence. And what else are we told? S1 is or S3 is 1. And between any two equal even integers, there can be only one odd integer. So things I'm noticing, one must go either here or here, although I don't think it's time to deal with that. So 1 in one of these spaces. And we'll keep it green, but only one odd integer here. Okay, I think that's the key, because we're going to have to stuff some, maybe even all of the even numbers in there. And then I think that will force a very particular pattern. So there are 7 spots between the 8s, and only one can be odd. So we need 6 even numbers. The other 6 must be even. But for an order 9 sequence, we only have 6 even numbers to deal with. The 2 6s, the 2 4s, and the 2 2s. Okay. And now we have to think, how can we arrange them in the gap between the 8s? So we'll just sort of zoom in. 1, 2, 3, 4, 5, 6, 7, 8, 9. 8 here, 8 here. The 2s have to have the 2s must be around the sole odd number, whatever it is. So we're going to have, let's use let's use the number sign we got there. So our odd number goes here. We have to have our 2s around here. The 4s must also go around. So we're going to have, and as luck would have it, with the 2s there, we have just enough to fit in between the 4s. So ultimately, the 6s have to go around it. The 2s have to be around it. The 4s have to go around it. The 8 has to go around it because it's the only odd number available. Because if the 2s were around some odd number and the 4s between them had another odd number, there'd be 2 odd numbers in between the 8s, and that would not be allowed. And if you feel like my justification is not enough, you could say you could write down what I verbally said. If there were 2 odd numbers, like the 4s were around a different odd number than the 2s, there would be 2 odd numbers in between the 8s, and that would not be allowed. Okay? So that can be perfectly fine reasoning right there, but I would say it's clear from here because we built it up. The 2s have to go around it, so it's got to be around the odd number. The 4s must also be around this odd number. If you want to, pick a fight over that one, that's fine. Add more justification. I get 6s, we get 4s. It's very interesting that we get this little nesting thing here. And I think this number is probably either going to be a 9 or 7 just because... Well, actually, no, it could be a 5, couldn't it? This number could be a 5. But I think the next thing to focus on is what is this number. So it must be odd. Let's take a look at our whole... I keep wanting to say kebab, but the whole golem sequence, that's what these are, golem sequences. So we get 8, 6, 4, 2, whatever this thing is. 2, 4, 6, 8. We know 1's got to be here, or 1 is in one of those 2 locations. And this is all we've got so far. So, what can go here? Or... we're running out of space for the 9s, actually. We are. I was going to say let's focus on this, but then I remembered, how did we go about a part? We didn't say, oh, what's this number got to be here, what's this number? We started by saying, let's place those 4s, because they're the big ones. They're the ones who need the most space or delicacy when we place them. And then when we got to the 3s, there were problems with the 3s. At least one idea for 3s just didn't work out. So I think we have 2 options at this point. Either try and work out possibilities for this number, or maybe go back to saying, where do the 9s have to go? Okay. I think I'm going to place the 9s, because I think if I start doing cases, like is this a 3, is this a 5, is this a 7, is this a 9, I'm going to wind up, and then my next step will be, okay, yeah, that could be a 5. Where can the 9s go? So I think I'm just going to jump to where can the 9s go. Where can the 9s go? That is a fantastic question. So we're going to ignore this number for a moment. I suspect he'll probably have to be either 9 or 7 just to fit the 9s in. Can the 9s go in here? We've got 1, 2. The indexes really help, actually. As I noticed with the 8s, because it was 10 and 18. So once I saw the 18, the 10 was really quick, because 18 minus 8 is 10. And the 9s, what is this one? 10, 11, 12, 13, 14. the 9s have to be 9 apart, and the 3 is actually used up, so we can ignore that one. But 9 and 1 aren't far enough apart. The only remaining pair of indices that are 9 apart are 5 and 14. Right? Because that does work. But, I mean, the next furthest away pair is 1 and 9, and that just isn't enough. It would have to be 1 and 10. So it's got to be 4 and 5 and 14. So now what have we got? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 8, 6, 4, 2, 9, 2, 4, 6, 8. We got the 1 here, and then the 9 has to go here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, yes, it did work. Alright, and now it is left for us to figure out the next thing. Well, we sort of solved 2 problems at once. I was going to ask if the 9s could have gone somewhere else, then the next question would be what's that number, but we worked out what that number was and dealt with the 9s at once. So I think the 7s. We gotta deal with the 7s now. I'm also starting to think in the back of my mind, because this has worked both for A part with placing the 4s and right now for placing those 9s. I'm thinking maybe for C part we try and place the widest or the biggest numbers or the biggest couple and see what happens there. Not quite sure on that yet, but just something that's working in the back of my head. I'm noticing a pattern. I'm noticing something that's been quite helpful to me. I don't think we have to go this way. I mean, certainly in A part, we could have placed the 1s first, or the 3s or something. But we placed the 4s, and now we've placed the 9s, and that helped us. And I'm about to place the 7s, so I think that might be a strategy for C. I don't know. I'll think about it. Okay. Next, let's place 7s. Can we place the 7? So another good thing I'm noticing here is counting the indices. Can only go in 1, 8 or 2, 9. So that didn't narrow it down quite as much as I want. Although if it goes in 2, 9, that forces the 1 here, and that could either be really good or really disastrous. Well, tell you what, we don't need the last half of this bit, so we can just focus on kebabbing the first 9. Not kebabbing, Skolem sequencing. 9 here, 6, 7, 8, 9. Okay, so we could either have the 7s here, and then what have we got? Well, we have to place the 3s somewhere. We have to place the 5s. Where could the 5s go? We could either have 1, 2, 3, 4, 5. And that would force this to be a 1, and then we'd have 1, 2, 3. So that works. Or we could have our 5s here. 1, 2, 3, 4, 5. That would force the 1 to go here, and then we'd be stuck with 2 3s. So with the 7s there, we can get 7, 5, 1, 1, 9, 3, 5, 7, 3, and then some more. The rest of the stuff. I think that one works. I want to double check these because I didn't do it with the indices. Maybe we should do it with the indices now. 4, 5, 6, 7, 8, 9. 9 minus 6 is 3. 8 minus 1 is 7. 7 minus 2 is 5. So yeah, this one does appear to work, along with the extra bits. Okay, so now, what else could we have? We could have the 7s in 2, 9. No, that's place 2, but no, we need the 7 there. So 7, 1, 9, and then we get 2, 3, 4, 5, 6, 7, 8, 9. Indices might be something that we care about, because I'm finding this a lot easier if I actually just write down the index numbers. Okay, so it forces the 1 to go here, and we could explain that if we wanted to. And then what could we have? Well, the 5s have to have 4 of them in the middle. The 5s have to go here. And then the 3s would go here. So that's a no-go. And you could explain it a bit more as well. So you could say something like 5s must go in 1/6. Indices are really helping. The 5s must go in 1/6, and that leaves 7 and 4. So 1 must go here. So no Skolem sequence. So I think, yeah. There's only 1? That's odd. The only such Skolem sequence is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Let's break up some of the bigger parts here. I think I need 5 in here. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm adding the indices not only just to count, make sure I got the right spaces, but I'm also going to do a little double check that this Skolem sequence does work. Seriously, go look up Langford kebabs. Go watch School of Hard Sums with Dara O'Brien. Anyway, 1 here. We're saying a 1 goes here. We're saying 7 here. 7 here. 9 goes here. The 3 has to go here. The 3 has to go here. And the 5s have to go here. So the 1s are 1 apart. The 2s are 2 apart. The 3s are 3 apart, 9 and 6. 4s are 4 apart. The 5s are 5 apart, 2 and 7. The 6s, 11 and 17, that's fine. The 7s, 1 and 8. The 8s, 10 and 18. The 9s, 5 and 14. And the 1 is in the 3 spot. There's only 1 odd number between any pair of equal even numbers. And the 18 is in the end spot. So this definitely is one that they want. And I believe we have ruled out any other possibilities. This is the only one that can happen. And it is a Skolem sequence. We just checked there at the end as well. And it's a good idea. Once you think you have a Skolem sequence, check it. Write out the indices and check it, because that's a great, quick way to say, does this actually work? Okay? I think that's it. And now we're on to C part, which was you can't have Skolem sequences of length whatever. Prove that no Skolem sequence of order n. Prove there is no Skolem sequence of order n if n is of the form. So when you divide it by 4, you get a 2 or a 3. And as I mentioned, Langford kebabs, I think it's a 1 and a 2. You can't have for the remainders. But it's interesting to see that they're connected. I wonder if you could make larger sequences where you had 3 n integers and there'd be 3 copies, and that'd be interesting. You'd sort of have them stapled onto one another. But back to the task at hand, C part. Prove there is no Skolem sequence of order n. Okay. So, I thought there were sort of 2 ways to do this. Or, I had 2 thoughts while doing B. One was, so for this we would say, okay, let's suppose n is 4k plus 2. Let's see if we can place the n's. And, there's only going to be so many places for that to go. And we could probably cut that in half with symmetry. And then we could say something like, okay, then where's the n minus 1s? And I think we'd probably run out of stuff to do. The issue being, I think that would be a little time consuming. I'm not ruling it out, But we'd have to do it, like, obviously if you're just looking at the ends, lots of different places you can place the ends, just like there were lots of different places to place the 4. And there were lots of places to place the 4s, and then once we'd done that, place the 3s. It was only when we got to the 2s and the 1s that things started messing up. So I'm betting that if this were to work, if we were able to generalize it like this, that, place the ends on the n-1s, and eventually you'll foul up, I would suspect it would take placing at least 4 for things to go haywire. Okay? That's my idea. And then we'd have to do that. So that'd be a lot of cases, and then we'd have to do that a second time with 4k plus 3. I'm not saying that's not what we're supposed to do, but it seems like pointless busy work. And for 10c, I'm expecting at least a more elegant way to do this. So what I'm thinking is, put that aside for a moment, and maybe concentrate not on the cases of putting things, can they go here, can this go here, can this go here, but maybe go back to the definitions, which are based on indices, and as you saw, I was liking having those indices there, because I could say, 18 minus 10, oh, okay, so that's for the 8s. So I'm thinking maybe we just go back to the definition. Maybe there is some numerical, algebraic, maybe some sort of situation. I'm thinking maybe squares. If I'm going to go down this way, I start to think, okay, what things do I know can't exist with mod 4 with remainders 2 and 3? And things that immediately pop into mind, there's no such thing as a square that when you divide it by 4 gives a remainder of 2 or 3. It can only be 0 or 1. So I'm thinking maybe some connection like that. But I don't know. I don't know. I don't even know where to start this. So I'm gonna. You guys don't have to watch me while I hem and haw about this. Why don't we? If we're just trying to do this with indices, and I don't know whether or not this will work, but we're just trying to do this with indices, and we don't want squares. I don't quite see how to get a square out of this. Other than, well, if you add up odd numbers, you get squares. My brain's just trying to make any connection it can, because really all I'm doing is staring at a definition. So I think maybe we should experiment with something. So they say we can't have one with 4k plus 2, so let's try and make one of size 2 and size 3. So maybe we will have to go with the placing. But what I'm going to do is I'm going to keep my options open with indices. So what I'm just going to experiment. This isn't part of my written solutions. I don't have to be super fancy. So if we had k is 0, and so we had 2 here. Well, let's place the 2s. We can either have the 2s here, or we can have the 2s here, and that just doesn't leave space for the 1s. That's not particularly exciting, and I can't really draw a whole lot of conclusions there. But now let's place the 3s for this one. We have the 3s here, we could have the 3s here, or we could have the 3s here. Now, before I place the 2s, because I don't want to do a whole bunch of casework if I can help it, right now I'm just experimenting, is there something I can notice with the indices? And is there something I can notice maybe with the indices of a Skolem sequence that does work? Because we had what? 4, 2, 3, 2, 4, 3 here, and 1 and 1. Just remembering that, I think that's the one they gave us. Yes, that is the one that they gave us. So, is there something I can notice with the indices here? Alright, well, nothing's immediately jumping out at me. So let's try the 3s here. I don't need to try that case because it's symmetry. Well, there's 2 spots for the 1s, and they exclude the 2s. And if we did this one, there's only 1 spot for the 1s, and that doesn't work for the 2s. It's looking like casework really is the way to go, and I wanted to avoid that. What else could we possibly do nk is if n is of the form 4k plus 2, 4k plus 3. Okay. What things wouldn't change if I just had a Skolem sequence? Suppose I did. I mean, that's how you got to go about doing this, right? That's how you got to go about doing these things. Is if you want to show something can't exist, you say, suppose I had one. That's rule number 1 of proof by contradiction, which is a fantastic technique. So I got to say to myself, what if I had one? Okay, what if we had such a sequence? Well, maybe we have to break it up into cases based on this, but what if we had such a sequence of 4k plus 2? What could we do? What wouldn't change that we could exploit? What blind observations could we make about such a sequence? Well, there'd have to be 2 of every integer. And the difference between indices would have to be k. Now, if there were 2 of every integer, I don't know, what could we do with that? So I'm thinking maybe we get a contradiction where we do something one way and do something with another way. This is really I'm really trying to avoid doing that casework, I'll be honest with you. And I know that if you get stuck like this and you think you do have one way that might work, you might as well do that. But I'm really not looking forward to it because it's a lot of placement and it's going to get more abstract. So I'm thinking there's got to be a better way. It really does. It's 10C for crying out loud. What things wouldn't change if I just had a Skolem sequence? Not a whole lot. The number of numbers wouldn't change. The sum of the numbers wouldn't change. What would be the sum of those numbers? It would be the sum of all the numbers from 1 to n twice, and that's n times n plus 1 over 2, so it would be n times n plus 1. And that's n squared plus n. Well, there's my square. But I don't see how to get a contradiction out of that. Unless we use something with the indices. Well, I know the sum of the indices. Got to relate the indices in some way to the actual k that they've got. That's got to be the issue. Problem is, I don't suppose. Okay, so might as well try and write at least some of this up. Suppose we had such a sequence. And what do they got? S1, S2, all the way up to Sn. Now, right now, there's nothing stopping such a Skolem sequence from existing. It's when we make n equal to 4n plus 2 or 4n plus 3 that something should goof. What can we do? So what could we do? We could find pairs ij. So Si is equal to Sj is equal to k for all k. But, I mean, that's just part of being a Skolem sequence. But we do know j minus I would have to be k, assuming I is less than j. And maybe there's something with that. Maybe there's some mathematical way to say you can't really cram them all in. I mean, that's what the casework would be doing, but maybe there's an elegant mathematical way to say it, fussing with these indices. And that's sort of what I'm trying to reach for here. Because it would be shorter to write. I mean, you're going to do that casework, you're going to be doing a lot of stuff. I mean, just look at those threes, the three case that we got up here. That was two separate things. Now try doing it with a generic 4k plus 2. You're not even you're gonna have so many cases. So that's really what I'm trying to illustrate when I want to avoid this. I mean, try and do it with 10. Just try and write out the cases of where to place the 10s for a Skolem sequence of order 10, and you'll see exactly what I'm trying to avoid. Okay, so if that's the case, then I guess what can we do? We can rearrange and say j is I plus k. And we're going to have well, okay. So, first of all, I have a typo here. It should be not to Sn, it should be S2n. I don't know, maybe if we add up the indices? Because you'd get 1 plus 2 plus all the way up to plus 2n, and that will be something. And that'll be 2n plus 1 all over 2. But in there, you're going to have sort of these I plus k things. I don't know. Let's let a I1 make more sense if I use proper notation. You want to count some indices, you use I's and J's. And let's let these be the lower indices so that Sk is equal to k, and Sik plus k is equal to k. So that's certainly a thing, but I'm not exactly liking where this is. So I don't know where to go with this anymore. So this sum here, we can get it in a different way. This would be, SI1, or so it'd be I1, it'd be 2I1 plus 1 plus 2I2 plus 2 plus 2I3 plus 3 all the way up to plus 2IN plus N. Right? Because we're going to have, if we add up these indices, we'll have one IK, another IK, so that's two IKs plus another K. So this will give me twice the sum of whatever the heck these numbers are, these indices, and I don't like this because I don't know what these are. These are too big of a variable. And then plus 1, plus 2, all the way up to plus n. Now that I am more comfortable with. So this is twice something plus n times n plus 1 over 2. And that's got to be equal to this guy over here. So, maybe the difference between these two can't be even? Is that it? Is that the big trick? Yeah, I don't want to keep writing out all these indices. First of all, they're annoying me because I don't know what they are, and it's driving me nuts because I think this can't be it's sort of like a warning light in my head. Too much variability, there's too much uncertainty, you can't do anything. So I'm going to let capital I be their sum. Okay, and then maybe this will make me a little more calm. So 2i is going to be 2n plus 1 all over 2 minus n plus 1 all over 2. Okay, so I can bring the 2 over to the other side, 4, and that actually is making me it's making me optimistic. Why? Because the things, the k's, the n's that they said wouldn't work were 4k plus something, 4k, so we should be working with factors of 4, multiples of 4, remainders 4, so seeing a 4i there makes me happy. Okay? That makes me feel like maybe I've stumbled onto something. I don't think we're there yet, but I think we're on the right track. So we'll have 2n plus 1 minus n plus 1. We can take out a factor n here. And we'll have 2 times, so it'll be 4n plus 2 minus n plus 1. So minus n minus 1. Okay, so n, 3n plus 1. So there we go. If n is odd, and that guy's even, but I don't think he's even enough. So for such a Skolem sequence, spell sequence properly, come on. We must have 4 has got to divide n 3n plus 1. And I could expand that out and we'd get some squares, but I think now is the time to bring back the cases. N is 4k plus 2, and 3n plus 1 is, I'm really hoping this works, 4k plus 2. Because we're just going to need to expand it out anyway, so no reason to make it 3n squared plus n. We'll have 12k plus 6 plus 1. So that'd be 4k plus 2, 12k plus 7, and that's going to have a plus 14 at the end. So 48k squared plus 24k plus 28k is 52k plus 14 which has a remainder of 2 when we divide by 4. And you could highlight that a bit more by saying 4 times 12k squared plus 13k plus 3 plus 2. So that would make it a bit more obvious. The point is, it's got a remainder of 2 when we divide by 4, so that means you can't do it. And now, the last case, I'm genuinely shocked because this actually seems a little easier than, say, 9 was. 9 I was stuck for a long time. This one I sort of stumbled upon an answer just by trying to avoid doing a whole bunch of other work. Despite the fact that my advice would usually be in that situation, do the other work. And maybe there is, in fact, a way to do this where you do say, suppose you had such a sequence, let's place the n's and the n minus 1s. But I'm trying to avoid that because I think that's going to be messy. I don't want to do that. But, on their past contests, which you have a link to, you can go see their solutions. Maybe they did this. Maybe they had something fancier. Although, come to think of it, being able to write off those indices and just say it's 4 times something is kind of slick. But, you know, sometimes they have 2 solutions, sometimes they have 3. Go see. Maybe they did something else. I'm curious. I might go after this video and take a look. Anyway, let's finish this thing off. So, well, at least I hope it finishes this thing off. This might not work. N times 3n plus 1 is 4k plus 3, because I think we're going to get, so we're going to have 12k plus 3, 12k plus 9 plus 1 is 10. You probably do this a lot quicker if you just did it all mod 4. If you're comfortable with mod 4, by all means write it that way. Anyway, 48k squared again. Now we'll have 40k plus 36k, so that'll be 76k. Multiples of 4 there. Plus 30, which is 4 times 12 squared plus 19. No, not 19. No, it is 19. I thought it was too low there for a second. Anyway, 19 plus 7 plus 2. Remainder of 2 when dividing by 4, or equal to, or congruent to 2 mod 4 is another way to say that. Dividing by 4. So no Skolem sequence. And that's what we were asked to prove. We did have to do those 2 cases separately. I don't think there was a fancier way to do that. But, and this middle part here, because I was just sort of messing around and saying what if, suppose if, could probably be cleaned up a little bit better. You might want to start by saying, here's a Skolem sequence, let these be the lower indices, and then, you know, write it up a little nicer and neater. But I'd say the gist of it's there, and actually I think that's one of the fastest times I've come to a solution after being stuck. Sort of flowed, and that makes for good question design. But, yeah, I think that's it. Proof if n is of those forms, we're fine. So, yeah, that does it for the 2004 Euclid. I'm done. I'm actually going to, as soon as I exit out of this, or close recording, I'm actually going to go see what sort of solution they had. Did they do a casework sort of thing? And, yeah, it could never hurt to read their solutions as well. I try and provide these videos so that you can see when I get stuck and how I think through them and how I get unstuck and that sort of thing, or to provide alternate solutions if I've done it some way different. But that's the 2004 Euclid. 2005 Euclid will be the next, will be sort of the cap for the next one, because I'm going to be moving on to year 2005. Thank you, as always, for watching, and if you want to do any of the fun stuff like comment or subscribe, by all means do that. Go ahead, and I will see you for whatever math videos there are in the future. So long for now.